Okay, continuing on with chapter 16, we're beginning in chapter 16.7. We started this chapter talking about conjugates. We labeled Bronsted-Lowry acids, and we labeled a Bronsted-Lowry base. Recall doing this at the beginning of the chapter. And we labeled things like in this example, hydrochloric acid is the Bronsted-Lowry acid. Water is the Bronsted-Lowry base. And the hydrochloric acid has a conjugate base, which is the chloride, because acids donate protons, and the Bronsted-Lowry base has a conjugate acid, which is the hydronium ion. Well, since we're labeling this as a base, we need to talk about its strength as a base, because it does have the word base in it. Since hydrochloric acid is a strong base, this reaction goes one direction. So the reverse reaction does not happen. That means chloride has no strength as a base. We would consider it a rather weak conjugate base. So any solution that has a chloride in it, like for example sodium chloride, the chloride's there, which is the conjugate base. It's not going to do anything to the pH because it's such a weak conjugate base. Now, that statement is the case for any conjugate base of a strong acid. Okay, so conjugate bases of strong acids, they have no strength as a base. Let's consider, however, the conjugate base of a weak acid. The weak acid we often use is hydrofluoric acid, and without even writing a reaction for that, you should know and be able to identify what the conjugate base is. You simply take away a hydrogen ion, and fluoride is the conjugate base. Because hydrofluoric acid is a weak acid, and someone asked this in our conference call earlier, you know things are a weak acid. I mean, you should be familiar with the strong and the weak, but also you've got a table of Ka values, and you always have access to that table. It's in your book, and y'all, even if we were on campus, when I do the test, I photocopy the Ka and Kb table and give that to you for the test. So you know if it's on that table, it's a weak acid. And to get the conjugate bases of those, you simply take away a hydrogen ion. Okay, now I'm going to write out a hydrofluoric acid equation reacting with water showing hydrofluoric acid behaving as an acid. You guys can do that? This would be that equation. And this is an equilibrium equation. And equilibrium equations have equilibrium constant expressions, right, for the Ka. Products over reactants raised to the power of the coefficient. Now, let's write another equation showing the fluoride ion behaving as a base. So write an equation for the fluoride ion reacting with water to behave as a base. Pause it and then turn it back on and see if this is what you wrote. Okay, because in this equation, the fluoride ion is accepting a hydrogen from water. It's behaving as a base. Its equilibrium constant expression, and it's a Kb also because it's producing hydroxide ions, would look like this. Again, we're leaving out water because it's a liquid. Okay? Now, guys, if I were to add these two equations together, if I were to take this balanced equation and this balanced equation and add them together, what would that look like? The fluoride ions would cancel out. The hydrofluoric acid would cancel out. And I would be left with two waters yields, I didn't mean to put it in square brackets, the hydronium ion and the hydroxide ion. And that should look familiar because that is the KW equation. KW, if you'll remember, is always the same number, 1 times 10 to the minus 14. It's just over 1 or over nothing. So what we've done here is derived a formula that the KW, which is 1 times 10 to the minus 14, is equal to the Ka times the Kb. Because if you were to multiply these two expressions together, it would give you this. Okay, because the HFs would cancel when you multiplied and the fluoride would cancel when you multiplied. So it's a new formula in all those formulas we have that KW is equal to the Ka times the Kb. So look up the Ka for hydrofluoric acid and let's calculate the Kb for the fluoride ion. If Kw is equal to Ka times Kb, Kw is always 1 times 10 to the minus 14. The Ka for hydrofluoric acid is 7.1 times 10 to the minus 4. And we can solve for Kb. And the Kb is 1.4 times 10 to the minus 11. And y'all will recall, I'm sure, that those are unitless. Okay? The same situation applies to where if we were doing a Kb, for example, ammonia. What's the formula for ammonia? Ammonia is a base. You would know that because it's on the weak base. It's on the list of KBs on the weak base table. What's its conjugate acid? It's the ammonium ion. So can you calculate the Ka for that? For the ammonium ion. I've got 5.6 times 10 to the minus 10. Okay, and there's more practice with doing that in your book on page 749. It's sample 16.17 is on page 748. It's actually where that starts. And then on page 749, there's some checkpoints that go along with 16.7. Okay, the next section, which is 16.8, I'm actually going to skip that. I'm not going to come back to it. I'm not going to do diprotic and polyprotic calculations. I'm going to do 16.10 now. I'm going to come back. Let's see. We're going to omit that section. That says omit. 16.9, we're going to cover that later. I'm going to do 16.10 now. Acid-base properties of salt solution, because it's going to tie better into what we just did. Okay, so you're probably going to want to get in your book and go over what I'm telling you and practice some of these, but y'all will remember from Chem 1 that an acid plus a base, it's kind of like that double exchange reaction, you know, if you could imagine me taking my hands and you're swapping the cations. An acid plus a base will produce a salt and water. And the first thing we're going to look at is predicting the pH of the salt. Salts can have an acidic pH, a neutral pH, or a basic pH. So first we're going to look at how you can look at formulas and predict, oh, that should be an acidic salt or a basic salt or a neutral salt. And then we're going to look at how you would calculate that. I think it's a good idea to predict it first so you know what you're expecting in your calculations. Okay, the first example, let's talk about neutral salt because those are easy. How do you know when it's going to be a neutral salt? In other words, the pH is going to be equal to 7. If you take a strong acid and a strong base, the salt is always neutral. Hydrochloric acid is a strong acid. Remember, the strong bases are group 1 hydroxides and heavy group 2s. What salt do these make? They make sodium chloride is the salt and water. Okay, this would be a neutral salt. It would have a pH of 7. Okay, we have to consider why it's neutral though. And considering why it's neutral goes back. I'm about to jump slides. You guys look up in your notes. Why it's neutral goes back to here. The salt contains the chloride ion. If you'll remember, I told you guys this reaction will not happen in reverse. The chloride ion will not take a hydrogen from water. That's the case of any conjugate of a strong acid. It's not going to take a chloride ion from water. Likewise, any group 1 element, because those are in strong bases, those do not break water off. They won't take hydroxides from water. So when we're considering why is this neutral, it's because if you put the chloride ion with water, this will not happen. And if you put the sodium ion with water, this will not happen because these are conjugates of strong stuff. Okay? So because we have a limited number of strong acids, there's 7, and we have a limited number of strong bases, when we look at the group 1 and the heavy group 2, there's actually a limited number of neutral salts. So, like if you named another strong acid and another strong base, that salt would always be neutral. Neutral salts to me are the easiest ones to pick out. Okay? Next, let's talk about a basic salt. Well, a weak acid plus a strong base produce a basic salt. Now, it's normal to say, well, if the acid's weak and the base is strong, then the fact that the salt is basic makes sense because it's like the strong base is stronger. But this strong base is not why the salt is basic. Let me show you. If we use as our example hydrofluoric acid, and for a strong base, we've used sodium hydroxide already, so let's do another one like potassium hydroxide. You should know the products for those. Potassium fluoride and water. to consider why is the salt basic. It's basic because of the fluoride ion. Because the fluoride ion is the conjugate base of a weak acid. So the reason it's basic is because if you have this fluoride ion in water, the fluoride ion can take a hydrogen away from water and leave water as a hydroxide. That's why it's a basic salt. So do you see, it's common, and it'll work for you to look at this and say, oh, this is stronger, that's why it's basic. But the reason it's basic, it doesn't have anything to do with the strong base. The reason it's basic is because of the conjugate base of the weak acid, taking the hydrogen from water. And likewise, if we considered, what about the potassium ion? Well, see, it's a group 1 metal. The potassium ion in water, it's not going to do anything. Group 1 metals completely dissolve in water. It's not going to take, this is not going to happen. Okay, so now let's talk about an acidic salt. And if you look at your notes, I'll bet you guys could do the acid-base thing. A strong acid plus a weak base would make an acidic salt. And again, it's okay to say, oh, well, this is stronger. That's why the salt ends up being an acidic. That'll help you to predict it, but it won't help you in explaining the why of what's going on. So like a strong acid is, let's do nitric acid. And these don't always produce water, okay, when it's a weak base. For the weak base, let's use ammonia because it's a simple one. This actually makes ammonium nitrate. Okay? Do you see that this still behaved as an acid because it gave the hydrogen to the ammonia, which was the Bronsted-Lowry base? And so, why is this salt acidic? It's not because of the nitrate, because the nitrate came from a strong acid. So the nitrate is not what made it acidic. What made it acidic is the ammonium ion. Because that ammonium ion in water, can you write that ammonium ion behaving as an acid? If it behaves as an acid, it has to lose a hydrogen. And it produces hydronium ions. And that is why it's an acidic salt. Okay, there's some more practice. There's some practice on doing these predictions on in your book on page 760. It's sample problem 16.22. So that's practice with the predictions. But what I want to do is look at the calculations of it. Okay, how could you, like we can maybe, with my explanation, look at this and say, oh, I'm going to predict that salt's going to be acidic, but let's calculate the pH. In order to do that, we're going to need to know the concentration of it. So the problem might say, calculate the pH of 0.10 molar ammonium nitrate. Okay, so that's all the problem's going to tell you. First off, you would have to recognize that as a salt. Okay, how are you going to know it's a salt? Well, a simple way, if you look at your weak acid table, it's not on there. hopefully you guys would look at that and say it doesn't look like any acid formula. Maybe it's one of those weird weak bases, but if you look at the weak base table, it's not on there. So we know it's a salt. And then maybe you would go through predicting what we just went over and look at, what would make ammonium nitrate? Well, I know nitric acid and ammonia would. And from that, we know this is weak. This is strong. So I'm going to predict that this is going to be an acidic salt. So I'm looking at a pH of less than 7 before I get started. So what makes the salt acidic? It's because ammonium is the conjugate base. Of a weak acid. Okay, this is a KB equation. And you don't have to write all that I'm writing, but I'm writing this to show you that the products over the reactants and I just started writing it all wrong. I started out right, but I wrote hydroxide instead of hydronium. It's a Ka equation. That looks like that. Okay. Anytime I'm doing the pH of a salt, I have to look up an equilibrium constant on a table. So for this case, because this is the weak one, I'm going to look up the Kb on the table. The Kb for ammonia is 1.8 times 10 to the minus 5. Anytime it's a salt, I have to do this. I don't use what I look up on the table. Whether I look up the Kb or I look up the Ka, I have to convert to the other one. Okay, so I'm going to do what we just did, and I'm going to convert that to the Ka, which I have. Is this one we did earlier? Yeah, 5.6 times 10 to the minus 10. And from here, guys, it should look familiar. We go to this equation that the Ka is equal to x squared divided by the initial concentration of the salt minus x. We still get rid of the little minus x. And so the Ka is 5.6 times 10 to the minus 10 is equal to x squared divided by 0.10. And we solve for x. X is 7.48 times 10 to the minus 6 molar. What is X equal to? Anytime you're using a Ka, X is your hydrogen ion. See? Hydronium ion, same thing as hydrogen ion. So anytime you're using a Ka, the X is equal to the hydrogen ion. So how would I calculate the pH? I simply take the negative log of that. And for the pH of this salt, I get 5.13 or 5.1, which matches what I predicted at the start, that it would be less than 7. Okay, so that's calculating the pH of an acidic salt. Now, let's do another one. Let's calculate the pH of 0.20 molar potassium nitrate. What acid and what base combine to make potassium nitrate? What acid made this? Nitric acid. What base provided the potassium? Potassium hydroxide. What kind of acid is that? Strong or weak? What kind of base is that? Strong or weak? Strong base, strong acid. So how would you calculate the pH of this? You don't have to calculate it. You know that the pH is 7. Okay. Let's calculate the pH of 0.15 molar lithium fluoride. It's a salt. What acid and what base made this? Lithium hydroxide, hydrofluoric acid. This is strong. This is weak. That means the salt is going to have a pH above 7. Okay, it's a salt, so what do? Which one of these am I going to look up on the table? You only have a table of weak stuff, so you're going to look up the Ka. The Ka for hydrofluoric acid is 7.1 times 10 to the minus 4. But what you're dealing with is not hydrofluoric acid, it's the fluoride of it. So it's not the HF, it's the F negative. F negative is the conjugate base. So you don't need the Ka, you need to convert to Kb. How do you do that? Kw divided by Ka will give you the Kb. So the Kb is 1.41 times 10 to the minus 11. And then if you'll remember from there, it picks up like normal. You take the Ka or the Kb. In this case, we're going to take the Kb is equal to x squared divided by the initial concentration of the salt minus x. We're going to assume that's small. And so therefore we can eliminate it. So we'll say 1.41 times 10 to the minus 11 is equal to x squared divided by 0.15, and we're going to solve for x. And for x, I get 1.45 times 10 to the minus 6. What is x telling you? It's telling you the concentration of something. What is it the concentration of? Anytime you use a Kb, X is always the hydroxide ion. That means when I take the negative log of this, I'll have the POH, which is 5.84, and I have to subtract that from 14 to get the pH, which is 8.16, which fits my prediction that it would be a basic salt. The pH would be above 7. Okay? That covers section 16.10. So page 756 and 757 in your book, there's some more practice problems with that. And y'all, all these videos I'm doing are new videos. So all those other YouTube videos that you could always go in and access, to see me doing other examples with classes in the past, those are still there. So know that y'all can still look at that. Now, I had said before we started doing this that we were going to come back and do section 16.9 later. So let's wrap up this chapter by covering section 16.9, which looks at the molecular structure and how strong the acid is. And guys, honestly, you could probably read this section and understand it just as well as me explaining it to you. But I'm still going to explain it. All right, the first group of acids we have are known as hydrohallic acids. If you'll remember, the halides are group 17 from the periodic table. Okay, And group 17 from the periodic table is fluorine, chlorine, bromine, iodine. And so the acids formed here are HF, HCl, HBr, and HI. Okay? Of these acids, you guys know that this is a weak acid. So the trend here is that acid strength increases the further down the periodic table you go. The reason for that is because the strength of the bond. Or you could also say the weakness of the bond. In order for HI to be a very strong acid, then what that means is that this bond is actually very weak. So this is a bond, okay? That means for it to be a strong acid, see, this happens very easily because strong acids completely ionize. So what that means on the other end of the spectrum, if we're looking up here at HF, that the bond here is actually a little bit stronger. See, that's what makes this a weaker acid and makes this an equilibrium. Okay, so that's how it works with the hydrohallic acids. The next group we look at are called oxoacids. Okay, and oxoacids are obviously acids that contain oxygen. We also, when I teach these in Chem 1, teach y'all how to name them, I call them polyatomic acids because it's acids formed from polyatomic ions. The first set we're going to look at is what's going on here. Like if you take nitric acid and nitrous acid. Now, y'all should know which one is stronger because one of those is on the list of strong acids. This is stronger. Why is it stronger? Well, if it has more oxygens in it, it makes the acid stronger because what all of those oxygens are doing, they disrupt the bond between the hydrogen. Well, it's not there. It's between the hydrogen and the oxygen. So, for example, and there's Lewis structures for these. For these two acids, all of these oxygens, they pull the electrons this way, making this bond easier to break. That's still happening here, but there's not as many oxygens, so this bond's a little, it doesn't break as easily. And breaking this bond is what makes the acid be stronger. Okay, the other thing to consider, so these acids were easy because they had, see, their central atoms the same. Both of them have nitrogen in the center. So if the central atom's the same, you just look at the number of oxygens. But what if you're comparing acids where, say, the central atom is different? Like this is chloric acid. And this is bromic acid. They have the same number of oxygens, so it's easy to point out that the difference in their acid strength is because of the difference between the chlorine and the bromine. And all you have to do in that case is look at electronegativity. Which one's more electronegative? Chlorine is more electronegative. That means this is going to be the stronger acid because the more electronegative is going to pull the electrons away, making that bond easier to break. Okay? I will not ask you to compare a combination of these two. So you're not going to be asked to say compare something where not only is the central atom different, but also the number of oxygens is different. Okay? So we're not going to do that kind of comparison. As far as molecular structure. Really what you would do, because you would just look up, well, you would know this one's on the strong list, and so it would be stronger. But if they were both on the weak list, you just look up the Kas. And the larger the Ka, the stronger the acid. Okay? So, that covers all of chapter 16. It's a pretty heavy chapter. I think you guys would agree. Not just because you're not able to ask questions in real time as you hear it, but pH and acids and bases. It's a lot to it. So I'm going to give you some end of chapter problems to work. These start on page 770. They are numbers 3, 5, 15, 25, 27, 29, 39, 43, 53, 55, 61, 71, 73, 79. Oh, I have more. 95, 103, 105, 107. Okay, so you can work those. We'll do another conference, one of those web conferences, and I can pick some different times, but y'all, if you have questions on them, you can bring those with you then or email me about them, anything.